Hello friends, in this video we shall learn generalized mean value theorem, that is Taylor's theorem. Dear friend, if you are new to this channel, please subscribe the channel and don't forget to press bell icon so that you can get updates of this channel, Taylor's theorem. We shall see the statement of Taylor's theorem. Let fn minus 1 be the n minus 1th derivative of the function f, which is continuous in closed interval a plus h, and fn be the nth derivative. Fn, the nth derivative, exists in open interval a plus h, and p be a given positive integer. Then there exists at least one number theta lying between 0 and 1, such that f of a plus h equal to f of a plus h by 1 factorial f dash a plus h square by 2 factorial f double dash a plus so on h raised to n minus 1 divided by n minus 1 factorial f n minus 1 a plus rn, where rn is remainder after nth term, which is h raised to n 1 into 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h, where theta lies between 0 and 1. This is the statement of Taylor's theorem. We shall revise the statement again. Let fn minus 1 be the n minus 1th derivative of the function f, which is continuous in closed interval a plus h. And this is the first condition. And fn, the nth derivative, exists in open interval a plus h. This is second condition. And such that a number p is a given, p is a positive number. For these three conditions, there exists at least one number theta lying between 0 and 1, such that f of a plus h equal to f of a plus h by 1 factorial f dash a plus h square by 2 factorial f double dash a plus so on h raised to n minus 1, that is n minus 1th derivative, h raised to n minus 1 divided by n minus 1 factorial into f n minus 1 a plus rn, where the remainder term rn is h raised to n 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h, that is nth derivative of the function at a point a plus theta h. We shall prove this theorem. F is a continuous function in closed interval a plus h given, such that f double dash fn minus 2 are continuous in closed interval a plus h, by the hypothesis that fn minus 1 is a continuous in closed interval a plus h. Since fn minus 1 is continuous, its all previous derivatives are also continuous. That's why f dash, f double dash, fn minus 2 all are continuous in closed interval a plus h. For the proof, we shall define a function phi as phi x equal to f of x plus a plus h minus x into f dash x plus a plus h minus x square divided by 2 factorial into f double dash x plus a plus h minus x cube by 3 factorial into f triple dash x plus so on. We shall define up to n minus 2 term a plus h minus x raised to n minus 2 divided by n minus 2 factorial into fn minus 2x plus a plus h minus x raised to n minus 1 divided by n minus 1 factorial fn minus 1x plus a plus h minus x raised to p into a. We shall define the function phi like this. Here the constant a is unknown. Then if we put x equal to a plus h in this above equation, we will get phi of a plus h equal to f of a plus h, and other terms will become 0. Because in other term x equal to, if we put x equal to a plus h, that becomes a plus h minus a plus h, that's 0. In all other terms it becomes 0. That's why we will get phi of a plus h equal to f of a plus h. Put x equal to a in 3, we will get phi of a equal to f of a plus h f dash a plus h square by factorial 2 f double dash a plus h cube by factorial 3 f triple dash a plus so on h raised to n minus 2 divided by n minus 2 factorial fn minus 2a plus h raised to n minus 1 by n minus 1 factorial into fn minus 1a plus h raised to p into a. Equation number 5 we will obtain from equation 3 by substituting x equal to a, and in 3 by substituting x equal to a plus h we will get equation 4 phi of a plus h equal to f of a plus h. We shall choose a constant capital A such that phi of a equal to phi of a plus h. That is, by equating equations 4 and 5, we will get f of a plus h equal to phi of a plus h equal to phi of a, and phi of a is nothing but, by equation 5, phi of a is nothing but f of a plus h f dash a plus h square by factorial 2 into f double dash a plus h cube by factorial 3 into f triple dash a plus so on h raised to n minus 2 divided by n minus 2 factorial fn minus 2a plus h raised to n minus 1 divided by n minus 1 factorial fn minus 1a plus h raised to p a. We define first phi, then put phi equal to a plus h, we will get equation 4. Then put x equal to a plus h in that equation, we will get phi of a plus h equal to f of a plus h. Then put x equal to a, we will get phi of a. Then by equating 4 and 5, we will get equation 6. The new function phi is continuous in closed interval a plus h, because it is a polynomial function. It is a derivable in open interval a plus h, and we have taken phi of a equal to phi of a plus h. This says that phi satisfies all the conditions of Rolle's theorem, and by Rolle's theorem, if phi is a continuous function in closed interval, derivable function in open interval, and phi is equal at extreme points, that is phi of a equal to phi of a plus h, then there exists at least one point C in the interval a plus h such that phi dash c equal to phi dash a plus theta h, phi dash c equal to phi dash a plus theta h equal to 0. Differentiate equation 3, we will get phi dash equal to f dash minus f dash plus a plus h minus x f double dash plus 2a plus h minus x divided by 2 factorial into minus 1 f double dash x plus a plus h minus x square by factorial 2 into f triple dash plus 3a plus h minus x square by 3 factorial into minus 1 into f triple dash plus so on n minus 2 a plus h minus x raised to n minus 3 divided by n minus 2 factorial into minus 1 fn minus 2x plus a plus h minus x raised to n minus 2 divided by n minus 2 factorial into fn minus 1x. In every term, we have used UV rule and differentiate that term, and we will get this phi dash. If we simplify this, we will get phi dash x equal to a plus h minus x raised to n minus 1 divided by n minus 1 factorial into fn x minus p into a plus h minus x raised to p minus 1 into a. As phi dash a plus theta h equal to 0, we shall replace x by a plus theta h. We will get a plus h minus a plus theta h raised to n minus 1 divided by n minus 1 factorial into fn a plus theta h minus p into a plus h minus a plus theta h raised to p minus 1 into a. This shows h raised to n minus 1 divided by n minus 1 factorial into 1 minus theta raised to n minus 1 into fn a plus theta h. Simplifying this term, and minus p into capital A into h raised to p minus 1, where a equal to h raised to n minus p, 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h, where h is not equal to 0, 1 minus theta is non-zero. Substituting capital A from 7 in equation 6, we will get f of a plus h equal to f of a plus h f dash a plus h square by factorial 2 f double dash a plus h cube by factorial 3 f triple dash a plus so on h raised to n minus 2 divided by n minus 2 factorial fn minus 2a plus h raised to n minus 1 divided by n minus 1 factorial fn minus 1a plus h raised to p into h raised to n minus p into 1 minus theta raised to n minus p divided by n minus 1 factorial into p. This is the value of capital A into fn a plus theta h. Simplifying these terms, we will get f of a plus h equal to phi of a plus h. Phi of a plus h is taken as phi of a, and that is nothing but f of a plus h f dash a plus h square by factorial 2 f double dash a plus h cube by factorial 3 f triple dash a plus so on. H raised to n minus 1 divided by n minus 1 factor into fn minus 1a plus h raised to n into 1 minus why h raised to n, because h raised to p into h raised to n minus p becomes h raised to p plus n minus p. P get cancelled, that is h raised to n into 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h. Equation number 8 we obtain, where theta lies between 0 and 1. The term in 8 is called as Taylor's remainder after n terms Rn, and that is Taylor's theorem states that f of a plus h equal to f of a plus h f dash a plus h square by factorial 2 f double dash a plus h cube by factorial 3 f triple dash a plus so on. H raised to n minus 1 divided by n minus 1 factorial fn minus 1a plus Rn. This is the nth term after remainder Rn. And Rn is nothing but h raised to n 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h. Taylor's remainder after n terms Rn due to Solomich and Roche is h raised to n 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn a plus theta h. Different researchers find the different value of Rn. By Cauchy, he substituted p equal to 1. By substituting p equal to 1 in the remainder value given by Roche, he will obtain Rn equal to h raised to n 1 minus theta raised to n minus 1 divided by n minus 1 factorial fn a plus theta h. And Lagrange's value of Rn is obtained by substituting p equal to n in Roche's value. We will get Rn equal to h raised to n divided by n factorial into fn a plus theta h. Thus, different researchers obtain these values. Putting a plus h equal to x, that is nothing but h equal to x minus a in 8, that is in Taylor's theorem. We obtain another form of Taylor's theorem as fx equal to f of a plus x minus a f dash a plus x minus a bracket square of factorial 2 f double dash a plus x minus a cube by factorial 3 f triple dash a plus so on. X minus a raised to n minus 1 divided by n minus 1 factorial fn minus 1a plus x minus a raised to n 1 minus theta raised to n minus p divided by n minus 1 factorial into p fn a plus theta into x minus a. This is another form of Taylor's theorem by substituting h equal to x minus a. Here also theta lies between 0 to 1. Maclaurin's theorem. It is nothing but a special case of Taylor's theorem where a equal to 0. Thus, if we substitute a equal to 0 in above equation, that is in equation 9, we get Maclaurin's theorem. The Maclaurin's theorem is nothing but f of x equal to f of 0 plus x into f dash 0 plus x square by factorial 2 into f double dash 0 plus x cube by 3 factorial into f triple dash 0 plus x raised to n minus 1 divided by n minus 1 factorial fn minus 1 0 plus x raised to n into 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn theta x. This is obtained by substituting a equal to 0 in Taylor's theorem, that is in equation 9, by substituting x equal to 0. Here also theta lies between 0 to 1. Solomich remainder is given by Rn equal to x raised to n 1 minus theta raised to n minus p divided by n minus 1 factorial into p into fn theta x. While Lagrange's remainder for Maclaurin's theorem is by substituting p equal to n, we will get Rn equal to x raised to n divided by n factorial into fn theta x. If we put p equal to n, we will get this term 0 and 1 minus theta raised to 0 becomes 1. That's why Maclaurin's Lagrange remainder in Maclaurin's theorem is x raised to n by n factorial into fn theta x. Cauchy's remainder for Maclaurin's theorem, we shall put p equal to 1 in Solomich's remainder Rn equal to x raised to n 1 minus theta raised to n minus 1 divided by n minus 1 factorial fn theta x. Now we shall solve some problems by using Taylor's and Maclaurin's theorem. Take Maclaurin's theorem with Lagrange's form of remainder for fx equal to cos x. For fx equal to cos x, we have to write expansion of by using Maclaurin's theorem with Lagrange's form of remainder. Maclaurin's theorem with Lagrange's form of remainder is given by fx equal to f of 0 plus x into f dash 0 plus x square by factorial t into x square by factorial 2 into f double dash 0 plus x cube by factorial 3 into f triple dash 0 plus so on x raised to n minus 1 by n minus 1 factorial into fn minus 1 0 plus x raised to n by n factorial into fn theta x. Now we shall try to find out derivative of cos x. We know that by standard result, nth derivative of cos of ax plus b is nothing but a raised to n into cos of ax plus b plus n pi by 2 dn by dx raised to n, that is nth derivative of cos of ax plus b is a raised to n into cos of ax plus b plus n pi by 2. Therefore, here fx equal to cos x. Therefore, fn x equal to cos of x plus n pi by 2. At a equal to 0, fn 0 equal to cos of n pi by 2. By substituting x equal to 0, we will get cos of n pi by 2. And f of 0 equal to cos 0. Cos 0 is nothing but 1. F of 2n0 equal to cos of 2n pi by 2 equal to cos of n pi. And cos of n pi becomes minus 1 raised to n. F of 2n plus 1 0 equal to, that means odd term, cos of 2n plus 1 pi by 2. It is 0. That is f of 2n plus 1 0 is 0 and f of 2n0 equal to 1 minus 1 raised to n. F of 2n0 equal to minus 1 raised to n and f of 2n plus 1 0 is cos 0. By keeping in these terms in mind, we shall learn that coefficients of even powers of x will be minus 1 raised to n while coefficients of odd powers of x are 0. Substituting these values of fn0 in Taylor's Maclaurin's theorem, we will get fx equal to cos x equal to 1 plus 0 plus x square by factorial 2 into minus 1. Again 0 plus x raised to 4 by 4 factorial into minus 1 square plus 0 plus x raised to 6 by 6 factorial into minus 1 cube plus so on. We will get x raised to 2n by 2n factorial minus 1 raised to n plus x raised to 2n plus 1 by 2n plus 1 factorial into minus 1 raised to n plus 1 cos of theta x. And that is nothing but cos x equal to 1 minus x square by factorial 2 plus x raised to 4 by factorial 4 minus x raised to 6 by factorial 6 plus so on minus 1 raised to n x raised to 2n by 2n factorial and plus minus 1 raised to n plus 1 x raised to 2n plus 1 by 2n plus 1 factorial cos of theta x. This is the Maclaurin's expansion of the cos x. Example second. Verify Taylor's theorem for fx equal to 1 minus x raised to 5 by 2 with Lagrange's form of remainder up to 2 terms in the interval 0, 1. Here fx equal to 1 minus x raised to 5 by 2. And we have to check for the remainder up to 2 terms. Therefore, fx continuous in 0, 1. F dash x is a continuous in closed interval 0, 1. F double dash x is also differentiable in 0, 1 open interval. And fx satisfies the conditions of Taylor's theorem. In Taylor's theorem with Lagrange's form of remainder up to 2 terms, n equal to number of terms 2 equal to p and a equal to 0 and x equal to 1 where the interval is 0, 1. Therefore, fx equal to, by substituting a equal to 0, x equal to 1 and p equal to 2 in Taylor's theorem with Lagrange's form of remainder up to 2 terms, we will get fx equal to f of 0 plus x into f dash 0 plus x square by factorial into f double dash theta x, where theta lies between 0 to 1. Therefore, we need f dash and f double dash. Here f of 0 equal to 1 minus 0 raised to 5 by 2, that is 1. F dash x is minus 5 by 2 into 1 minus x raised to 3 by 2. F double dash is 5 by 2 into 3 by 2 into 1 minus x raised to 1 by 2. Therefore, f dash 0 is minus 5 by 2 and f double dash theta is 15 by 4 into 1 minus theta raised to 1 by 2. Substituting these values in this expansion, we get fx 0 equal to 1 plus 1 f of 0. 1 plus 1 into minus 5 by 2 plus 1 by 2 factorial into 15 by 4 into 1 minus theta raised to 1 by 2. Solving for theta, we will get theta equal to 9 by 25. 9 by 25 is nothing but 0.36. This value lies in the interval 0 and 1, and thus Taylor's theorem is verified. What we have to do? We have to expand, and by using the conditions given, find out value of theta and check whether that theta lies between the interval 0 to 1, the given interval. If theta lies in given interval, then Taylor's theorem is verified. If theta lies outside that of interval, then Taylor's theorem is not verified. Here, theta equal to 0.36 lies between 0 and 1, and hence Taylor's theorem is verified. Example 3rd. For every x greater than or equal to 0, show that 1 plus x square by factorial 2 is less than or equal to e raised to x is less than or equal to 1 plus x square by 2 into e raised to x. Here we shall use a Maclaurin's theorem with Lagrange's form of remainder for the function fx equal to e raised to x. As fx equal to e raised to x is given here, we shall take fx equal to e raised to x. By Maclaurin's theorem, we will get e raised to x equal to 1 plus x square by factorial 2 plus x cube by factorial 3 plus so on, x raised to n minus 1 by n minus 1 factorial plus x raised to n by n factorial into e raised to theta x, where theta lies between 0 to 1. Note that e raised to x and all other its derivatives are continuous for any x. All derivatives of e raised to x are e raised to x. Therefore, they are continuous. Taking remainder up to 2 terms, we get e raised to x equal to 1 plus x square by factorial 2 into e raised to theta x. For x greater than or equal to 0, theta lies between 0 to 1, e raised to theta x is less than or equal to e raised to x. So that the equation becomes 1 plus x square by factorial 2 e raised to theta x. This term is less than or equal to 1 plus x square by factorial 2 into e raised to x. Also, for x greater than or equal to 0, theta lies between 0 to 1, e raised to theta x is greater than 1. So that 1 plus x by x square by factorial 2 is less than or equal to 1 plus x square by factorial 2 into e raised to theta x. And that's why if we compile these two equations, two inequalities, we will get 1 plus x square by factorial 2 is less than or equal to 1 plus x square by factorial 2 into e raised to theta x, which is nothing but e raised to x is less than or equal to 1 plus x square by factorial 2 into e raised to x. Factorial 2 is nothing but 2, and that's why we will get the given inequality. If you like this video, subscribe the channel and press bell icon. Thank you. See you in next video.